Desalination as a tool for climate resilience. Desalination as a tool for climate resilience. As the impacts of climate change continue to escalate, the world is facing an urgent need to adapt to the changing environment and enhance its resilience against the growing challenges. Understanding the water scarcity challenge. Water scarcity is a complex issue that is exacerbated by climate change. As temperatures rise and precipitation patterns become unpredictable, many regions are experiencing reduced water availability. Traditional sources of fresh water, such as rivers, lakes, and groundwater, are facing increased stress, leading to water shortages for both urban populations and agriculture. In some cases, communities are forced to rely on unsustainable practices, depleting already strained water sources. Desalination, a viable solution. Desalination, the process of converting seawater into fresh water, has gained traction as a potential solution to address water scarcity challenges. Historically, desalination has been met with skepticism due to concerns about its environmental impact, energy requirements, and cost-effectiveness. However, advancements in technology and a growing understanding of sustainable practices have transformed desalination into a feasible and promising option for bolstering climate resilience. Types of desalination technologies. There are two primary desalination technologies: thermal desalination and membrane desalination. Thermal desalination involves heating seawater to generate steam, which is then condensed to produce fresh water. This method is energy-intensive and often relies on fossil fuels, raising environmental concerns. On the other hand, membrane desalination, particularly reverse osmosis, RO, has gained prominence due to its lower energy requirements and reduced environmental impact. RO uses semi-permeable membranes to separate salt and impurities from seawater, producing fresh water suitable for various uses. Energy efficiency and sustainability. Energy consumption has long been a drawback of desalination, but ongoing efforts to improve energy efficiency are changing this perception. Research and development in desalination technology have led to innovations that significantly reduce energy requirements, making desalination more sustainable. Renewable energy sources, such as solar and wind power, can be integrated into desalination processes to further mitigate environmental impacts and dependence on fossil fuels. Environmental considerations. Environmental concerns have played a pivotal role in shaping the evolution of desalination practices. Early desalination facilities had limited awareness of the potential impact on marine ecosystems, as the concentrated brine byproduct was often discharged back into the sea. This brine can have harmful effects on local marine life and ecosystems. Economic viability. Desalination was once considered economically prohibitive, but advancements in technology and economies of scale have transformed its affordability. Many regions facing severe water scarcity, such as arid coastal areas, are finding that the benefits of desalination outweigh the costs. The reduced reliance on traditional freshwater sources can lead to long-term economic savings, as well as reduced risks associated with water scarcity-induced disruptions to agriculture and industry. Desalination and climate resilience. Desalination serves as a critical tool for enhancing climate resilience in several ways. 1. Diversification of water sources. By tapping into the vast seawater reserves, communities can diversify their water sources and reduce dependence on rainfall and groundwater. This diversification improves overall water security and reduces vulnerability to changing precipitation patterns. 2. Emergency response. Desalination can play a crucial role in emergency situations, such as droughts or natural disasters, where traditional water sources may become compromised. It provides a reliable source of fresh water to meet essential needs during crises. 3. Agricultural sustainability. Agriculture is a major consumer of freshwater resources. Desalination can provide a lifeline to agricultural communities by ensuring a steady supply of water for irrigation, reducing the risk of crop failures due to water shortages. Challenges and the way forward. While desalination offers substantial benefits for climate resilience, there are still challenges that need to be addressed. 1. Environmental impact. Despite improvements, brine disposal remains an environmental concern. Research into alternative disposal methods and technologies is essential to minimize the impact on marine ecosystems. 2. Energy consumption. Although energy-efficient technologies are emerging, desalination still requires a significant amount of energy. The integration of renewable energy sources can help reduce the carbon footprint associated with the process. 3. Costs. While costs have decreased, desalination is still relatively expensive compared to traditional freshwater sources. Continued technological advancements and economies of scale are likely to drive down costs further. 4. Public perception. Ensuring public acceptance of desalination projects is crucial. Addressing concerns about the environmental and social impacts of desalination, as well as involving local communities in decision-making processes, can foster a more positive reception. Conclusion. Desalination has evolved from being a controversial and energy-intensive practice to a promising tool for climate resilience. As the impacts of climate change intensify, the availability of freshwater becomes increasingly uncertain. Desalination provides a solution to this challenge by offering a reliable and controllable source of freshwater, reducing the vulnerability of communities to water scarcity-induced disruptions. Sustainable integration and collaboration. The success of desalination as a tool for climate resilience hinges on a holistic approach that embraces sustainability and collaboration. To maximize the benefits of desalination while minimizing its drawbacks, several strategies can be employed. 1. Ecosystem-based approaches. Designing desalination plants with ecosystem-based considerations in mind can help mitigate the impact on local marine environments. Such approaches might include siting facilities in areas with minimal ecological sensitivity and implementing innovative brine disposal techniques that minimize harm to marine life. 2. Renewable energy integration. The integration of renewable energy sources, such as solar, wind, and tidal energy, can drastically reduce the carbon footprint associated with desalination. Hybrid systems that combine desalination with renewable energy production can offer a more sustainable and resilient solution. Government agencies, research institutions, and private sector companies should collaborate to drive innovation in this field.